So here's the script, it's running. And let's double check the recording is recording the channel correctly. Yep, it is.
Just out of curiosity.
Yep.
How come it does that? Your little command line. It's just like adding a little.
Oh, it's just reporting. It's just the status. I suppose I can make it quote unquote quiet and not to report this. It's basically saying how many seconds we have been recording, what is the average bit rate at this point, how big is the file. What type of frame rate are we talking about? Which frame are we talking about? That sort of thing.
Do you set it to do that, or it just does that?
No, that's the default.
It's like a ping, right? It's like a ping.
It's just reporting that it's doing something, and also giving you the current bit rate at the time, because in some cases you might want to know what is the current bit rate, so that you can kind of gauge.
ICMP. Yeah.
Well,
or you
it's
call
not
it something else in Linux.
No, this is really writing everything just to a file, so it's not bringing another server in anyway.
Oh, okay.
Yep. But according to this bit rate, it's basically for you divide it by 10, then you get the kilobytes per second rate. So this is about 400 kilobytes per second. That's how much space is consuming on a per second basis. 400 kilobytes per second. Which is not too bad. I mean, it's recording in relatively high resolution. Have you guys tried to stop a frame when it's in 720p mode, and see how clear the picture is? I mean, it's really quite clear. It's almost like lossless. Okay, so we'll go ahead and get started with this class. And I have to say the evening class attendance is much better than the morning class. I mean, the morning class will still be strolling in, like 15 minutes, 20 minutes past, the time.
What time does that class start out?
About 10, 10:30.
Wow.
So people will still be strolling in at about 10:45.
Everybody hugging their coffee mugs.
Yeah, that too. Okay, so what we'll do today is I'll take a really quick look at the IEEE magazine. It's basically it's online magazine. Ender's Game is already a reality for the U.S. military. Now that really brings up quite a few things that I think is related not only to this class, but also what is the future of computer science. The first thing is, does anyone know when Ender's Game was written? What was the year? 1985. Yep. There's no single correct answer in this case, because the story was actually written in the late 70s, but he basically reformatted the storyline. Right, or the current version was basically published in 85. So we are talking about a science fiction that's what, almost 30 years old, and we are finally catching up in terms of simulation technology. If you read the article, it has screenshots of what the Marine Corps is now going through, because they're subjecting all the soldiers to simulations now. It's less expensive and also safer in many ways when they're first just starting to get into the training. So it's kind of interesting in that way, but it's also interesting in a way that we can see that science fiction is not that far ahead of actual science and technology anymore. They used to be way ahead, right? I mean, if you read Jules Verne's, 20,000 Leagues Under the Sea, that was way ahead of its time. It has, it was at least 100 or 200 years, until before people can actually make submarines. But the concept was around, and then people just couldn't quite do it because the technology was not there yet. And now it's a lot, more progressing a lot faster. So that's really kind of interesting. And of course, we have Bitcoins. For those of you who know what it is, it's really interesting. It's really interesting
growing?
stuff. Huh?
Is that really growing?
Well, go ahead and read it, on your own and find out, what it is about.
Yeah, it is.
So that's, a little bit of, just news and, interesting things,
Hacker's delight.
Sorry?
That's going to be hacker's delight on that.
Oh, not just hacker, but also mafia. Anyone who wants to move money around, that's really the way to do it. The second thing I want to show, is newblocks.appinventor.mit.edu. we have already talked about enough concepts. So if you guys want to write apps and whatnot, you can actually go there and get started. This is a WYSIWYG way to make really simple apps, but you can make fairly complicated apps too. There's a certain restriction, so it's not general purpose app programming. I can show you how to do something relatively quickly. Okay, so
What did you say? Is it extra credit?
No. But it is something that might be useful for some of you if you want to write some apps and actually put it on the Google Play Market. So here's a blank screen. It's more or less what you see is what you get, and you can create an app just by dragging these components over. Like you can drag a button over, you can drag labels, images, slider, text boxes, and so on. It also has additional components, and if you want to deal with multimedia, there's camcorder, camera, image picker, player, sound, video player, and under animation you have a ball, and also an image sprite. So you can actually kind of do some sort of simple animation. You can program a sprite to go in a certain direction at a certain speed, and it will do it by itself. When it does collide with something else, it will generate an event. Then you can process that event. Under social, we have all the usual stuff, Twitter, texting, and so on. You can also, under sensing, you can have access to accelerometer, the location sensor, which is your GPS sensor, and also your orientation sensor, because you can tell how the device is oriented. Screen management, simple stuff. It's just how do you want to align components on the screen. This is really interesting for those of you who like robotics. You can get a Mindstorms NXT kit, and because your phone or mobile device is probably Bluetooth enabled, you can use Bluetooth to talk to your robot kit, and you can basically control every aspect of your NXT robot kit through a phone or Android application. And then there's other stuff which has all the kind of odd end stuff. Activity Starter doesn't look like it's a lot of fun, but it's really, really important, because what you can do is to have your app to start another app, okay? And that allows you to do a lot of interesting things. You can start up the Maps app in Android, and you can display the current location, and it's really quite useful. The Bluetooth client and Bluetooth server components allow you to communicate with other Bluetooth devices. And there's a lot of flexibility there. You can also have a web component, which means your app can actually talk to a website. And depending on whether you have control over on the other side, on the other side of the website, you can do some CGI scripting. Then you can actually have your app written in this form to communicate with the website, and then you can retrieve data remotely. You can store data remotely. And you can do a lot of really interesting stuff using this little engine. But what I think is the most interesting part is how you write your program. You go to blocks, and this is how you write your program. You do not type in this case. You drag and drop your entire program. Just about, not entirely, but just about. Okay, let's say I want my button to do something, okay? And under button, we have all these things that I can choose from, in order to do something. So if I want to say when the button is clicked, I want to do something, I drag this block out like this. And depending on what I want to do, let's say I want to keep a counter. Okay, that's as simple as it can get. So I can now go to variables, initialize a global variable to a particular value. So I can say this is my counter, and then it's complaining. Okay, it's trying to save the file, but it may be having problems doing that. But then I can go to my button here, and then I can go to variables again, set a variable. In this case, I can set my global variable to, let's say, its current value plus 1. So I can drag the plus operator here, go back to variables, go to get, and then click the variable that I want to use, and then drag a constant on the other side, change it to 1, and now we have a button. Then every time I click it, it will increment a counter by 1. It has all of the control structures that we have talked about in this class already. If you look under control, you have the typical conditional statement, like this one, except you can also add else if as many times as you want. You just drag the else if into the if, and now you can see that the block is getting longer and longer because it is becoming a multi-branch conditional statement. Okay? If you don't want it, you put it into the trash can. We have the for loop here. The for range loop is really kind of like a, it's the same kind of loop that we have been talking about, except it has a counter. It's built into it. We have the while loop here. Okay, this is our pre-checking loop. It does exactly the same thing as our usual pre-checking loop. It even has a null statement, which is to do nothing. Okay, you can plug that into a place where you can say, I don't want to do anything. So it's really quite interesting. I'm not going to go through this too much because it's really out of the scope of this class. But many of you at this point probably know enough to play with this already. Now the best part about this is you can run your app in an emulated Android device. So if you don't have an Android device, you don't need one. You can run it inside an emulator. On the other hand, if you have an Android device like a phone or a tablet or something like that, you can do this. You can package for phone and download this to this computer. That will give you an APK file, which is a file that you can use to distribute your application. And if you want to check out the projects of other people, you can go to Gallery. Now Gallery is really, really kind of fun because now you can see what other people have been doing with App Inventor. So you can see all the other apps that people have been making, Gangnam Style. And some of these are games, and some of these are just pieces of entertainment. But you can check out what other people have been doing, and not only to run their apps, because you can do that with Google Play also, but also you can look at the source code. Every project in the gallery has the source code available. So this is really a good way to learn how to do something, is to look at how somebody else is doing it, and then you just take in the technique and say, oh, so this is how we can get something done in a particular way. So I just want to expose, give you guys this exposure, and for those of you who want to kind of pursue this, because you really want to do some app programming, App Inventor is a good entry point. It's not complete in the sense that you can do any application that you want, but you can get a lot of interesting programs done this way too. So that is that. So getting back to today's class, the first thing I will do is to finish up the homework assignment, okay? Because we have array 2 that is due tonight. So we'll go ahead and take a look at array 2. I think I might have misplaced it. Is it in topic 8 or topic 6? It's definitely not there. So in topic 8.
Topic 4.
Is it topic 4?
Barely found.
And of course I can also cheat and just look
I
at
just go to assignments on the left there.
Yeah.
Somewhere.
assignments. Okay, under topic 4. Yep, array 2. There we go. Okay, so we'll first finish this homework assignment, so at least you will know what the answer is supposed to be. When I explained this to my morning class, I got an interesting feedback. One student told me it was too easy. This student was expecting it to be a little bit more difficult than the actual binary search algorithm, but it turns out to be quote unquote easier. And the student was a little bit suspicious of the program. It's like, is it really that easy? Okay, so we'll take a look. This log editing. Okay, let me do a save as. There we go. All right, so here is the wrong version of the binary search algorithm. It is wrong in 3 ways, not 2. There are 3 places where it is incorrect. Two would actually impact whether the algorithm exits or not. One would impact whether it can come to the right conclusion or not. As we go through the algorithm, I'll explain what those problems are and how it is impacting the algorithm itself. So it's time to trace it. And we'll start with sheet 2. Now sheet 2 is actually pretty easy, but sheet 3 is even easier because in this case we can actually find it. The algorithm actually completes. Precondition is all that stuff. If you don't type in pre, it's okay, no problem. On line 1 we initialize b to 0. On line 2 we initialize e to 3 because bar a bar is the number of elements. We got 4, and then bar a bar minus 1 is 3. Then we proceed to line 4. M is going to get a value. It's going to get b plus e, which is 0 plus 3, divided by 2. That will give us 1.5. The floor of 1.5 is 1 because it is the largest integer that is less than or equal to 1.5. Then we move on to line 5. We perform a comparison. A bracket m is referring to a bracket 1 because m equals 1 at this point. It has a value of 6. And we're comparing that to k, and k at this point has a value of 8. And the comparison is, the result is true. Okay. Then we move on to line 6. Line 6 is copying the value of m to b. M has a value of 1, so now b also has a value of 1. And then we get out of the conditional statement, we get to line 10. Line 10 has a disjunction to evaluate. A bracket m equals k is false. I don't even have to think about it because I haven't changed m, I haven't changed k, and I certainly have not changed anything in the array. So if a bracket m is less than k is true, it certainly cannot equal to k. So I don't even have to double check in this case. Now if the first condition of a disjunction is false, I have to evaluate the other condition because it's not enough for me to conclude the result of the entire disjunction. So now I have to go ahead and compare b and e. b is greater than e is also false because b has a value of 1, e has a value of 3 at this point. 1 is greater than 3 is false. Now we have false or false, which means the entire expression is false. That expression or that condition is our exit condition. When the exit condition is false, we have to go back because it's not time yet for us to get out of the loop. So we go back to line 4, and line 4 is going to recompute the value for variable m. This time we have 1 plus 3 divided by 2, which is 2, and then the floor of 2 is 2 itself. And then we go to line 5 again. A bracket m is less than k is false because this time a bracket m is a bracket 2, which has a value of 8. K has a value of 8. 8 is less than k is false. But in this case, we just go straight into line 8 because the else on line 7 is not an else if. It's not an else if. So we go to line 8, we change e. E gets the value of m. M has a value of 2 at this point, so e is getting a value of 2. Are we doing okay so far? Okay. And then we go to line 10. A bracket m equals k is true, and because we are using short-circuited Boolean expression evaluation, we don't even bother to evaluate the right-hand side because the left-hand side alone is enough to tell us that it is true. If you forget about short-circuited evaluation and you write out the entire expression and say the entire expression is true, I'm not going to take any points off because I did not explicitly say that you have to do it that way. Okay, and once the exit condition is true, we get to post, and we're all done. Any questions about this trace? Nope. Okay, moving on to the second test case, which is even easier. Because in this case, we only need one iteration, and then it will exit. On line 1, once again, b gets a value of 0. Line 2, e gets a value of 3. Line 4, m gets a value of 1. Line 5, a bracket m is a bracket 1. It has a value of 6. 6 is less than k, which also has a value of 6, is false. We go straight to line 8. Line 8 is copying the value of m into e, so e now ends up with a value of 1. We end up on line 10 after that. A bracket m equals k is true. The exit condition is true, so we get out of the loop, we get the post, we are done. And then the last one is the one that has a problem. Now, this is also another good example to show you why test cases by themselves may not be sufficient to show you whether an algorithm is correct or not, right? Because if I only gave you sheet 2 and sheet 3 to test the algorithm, then the conclusion is, yes, it works for both test cases. Okay? In other words, we haven't thrown a dart that lands on the red spot yet. But does that mean that there are no red spots in the circle? Nope. Okay? So now we'll basically land on a red dot at this point. The first few rows of traces are basically the same as last time, because line 1 is putting a value of 0 into B, line 2 is putting a value of 3 into E, and then line 4 is putting a value of 1 into M. And then we proceed to line 5. A bracket M is A bracket 1. It has a value of 6 at this point. 6 is less than K, which has a value of 10, is true. Okay, no problem. We go to line 6. B gets the value of M, so B is now updated to 1. We get out of the conditional statement. We get to line 10. A bracket M equals K is false because it is less than, it cannot be equal at the same time. Then we have to evaluate the other side, the right-hand side. B is greater than E is also false. We have false or false, so the whole thing is false. We go back to line 4. Okay. On line 4, we are going to recompute the value of M. This time it is 1 plus 3 divided by 2, which is 2, and then the floor of that is just 2. So M gets a new value of 2. We go to line 5. A bracket M is less than K this time is, it's still true because A bracket M is A bracket 2. It has a value of 8. 8 is less than 10 is true. Then we go to line 6 again. Line 6 is going to copy the value of M to E. So to B. So B ends up with a value of 2 at this point. And then we get to line 10. On line 10, A bracket M is less than K, equals K is false. We evaluate the other side, the right-hand side. B is greater than E is false as well. False or false is false. Now we go back to line 4. This is not the time yet to conclude that the algorithm would not end. Because at this point, I don't have enough evidence that this is an infinite loop. Okay? We have to go through one more iteration before we can make that conclusion. So on line 5, some of you probably already know what's going to happen here, so you just copy it and paste it. But in this case, let's pretend that I did not know. So on line 4, we will compute 2 plus 3, which is 5. 5 divided by 2 is 2.5. The floor of 2.5 is 2. So I still end up with the same value in M. Okay? But because the comparisons are all based on M, you will expect exactly the same result at this point. So A bracket M is less than K is going to be true because it was true in the previous iteration already when M was also 2. And then we go to line 6. Line 6 is going to copy the value of M to B, but we did that last time too, so B is just ending up with quote-unquote a new value of 2. And then we get to line 10, and of course nothing got changed, so that means A bracket M equals K is still false, B is greater than E is also false, and then the whole thing is false. At this point, you have enough information to conclude that this is an infinite loop, because when you look at the previous iteration, it looks like this. You look at the current iteration, it looks like this. Nothing has changed. Okay? If you go through one iteration that is identical to the previous iteration, especially in programs like this, then you can make a conclusion that nothing is going to change, and as a result, the program or the loop will never exit. Now, that type of reasoning only applies when the variables are only affected by this particular program. There are cases where your variables can be affected by something else. What do you mean by something else? I mean, this is the whole program. How can a variable be affected by things that are outside of this program? what if your variables are getting something from a query to a database? Well, your database can be accessed or updated by another program that is running what we call asynchronously, which means the two programs are not running in a synchronous way. So the other program could have updated entries in the database while your program or while this algorithm is running. So in those cases, you cannot say, oh, I have two iterations, they have exactly the same value, and therefore this is an infinite loop, because something else can cause changes that your program is not aware of, and as a result, your code can get impacted. All right. Are there any questions about this program? So at this point, I can make a conclusion and say, this is an infinite loop because nothing got changed in the last two iterations. That's good enough as an explanation. Okay. Any questions about the third test case in this for this particular algorithm? No questions? This is all good? Okay. So with that out of the way, we are going to proceed and talk about local variables. Remember last time, we were talking about the use of global variables, which is the only type of variables that we know of at this point. Okay. The characteristics of a global variable is it is global. Okay, what does that mean? Each variable is visible to the entire algorithm. There's no limitations whatsoever. But because of that, we also have problems, because now if you have two subroutines making use of the same global variable, then we have a problem, because the subroutines do not know that they are all accessing the same variables, the same global variable. We talked about cheesy ways to fix the problem, remember? Okay, if I use variable I as a loop control variable in one subroutine, I'll just use j in the other one. Well, that works okay when you have 2 or 3 subroutines. But what if you have thousands of subroutines? Now, who would be insane enough to write programs that have thousands of subroutines? But just about any useful programs have thousands of subroutines. Okay, so it's not like it is unlikely to happen. It is actually very likely to happen that you have thousands of subroutines. We also talked about the other cheesy approach to fix the problem. We'll use the name of the subroutine as a prefix. Okay, and then we'll declare the variable name as a prefix and then the name of the variable. But that is not a good approach either, because if I have a typo, if I copy and paste my code and I forgot to change the name or the prefix, I can still end up using the same global variable in multiple subroutines. In fact, that would make it really hard to find where the problem is. So the correct solution is to use local variables. Okay, so we'll go take a look at a program that makes use of local variables and see how that is going to change the behavior of our programs. So I'm going to close all of this stuff first and then start with a new spreadsheet. Okay, let's not do any recovery. And here is my new program. Okay, this is not going to be the same program that we looked at before. Instead, I'm going to make a new program that is, its only purpose is to illustrate the use of local variables. So we'll go ahead and do something like this. Okay, I'll call this useless. The name of the subroutine is useless because it is useless. Okay, so useless is going to do something like this. It is going to declare that we have a local variable, a variable that is local to useless. Okay, we'll call that, let's call it L, okay, uppercase L. And the only thing we do inside useless is L gets a value from another variable. In this case, X is a global variable. And then we'll say, oh, let's do something fun with L. Let's double the value of L. So we're actually doing something with it. And then we basically say, and the subroutine. And then outside of the subroutine, we say, okay, let's let the global variable x start with a particular value. We'll make it start with, let's say 10. Okay, it doesn't even matter what it is. And then we'll invoke useless. And then we'll see what happens. Okay, we'll try to see why useless is useless. Once again, the purpose of this entire algorithm is just to show you what a local variable is, and that's why there's no particular purpose to this program. We'll open a new window, go to another sheet, and then we'll take a look at what happens when we trace this program. We don't need comments because there are no conditions to evaluate. We do have line number as usual, and we have one variable from the get-go. We only have x to deal with. That's because, you guys have any questions? Okay. That is because, one difference between a global variable and a local variable is their lifespan is entirely different. A global variable starts existing as soon as your program runs, and it will cease to exist only when your program is getting to post, when your entire program is done. When you're talking about local variables, they do not even exist until you invoke the subroutine that has that local variable. So that's the lifespan of a local variable. It does not even exist until the subroutine is invoked. So at this point, I'm still talking about the precondition of the entire program. So L as a local variable does not even exist at this point. I cannot even tell you which column is going to be L because L does not even exist. Okay. Now, because it doesn't exist, that also means on line 6 and line 7, there's no way for me to refer to the local variable L because the other attribute of a local variable is it is only visible within the subroutine that contains it. So in this case, local variable L is defined inside useless, so that means only useless as a subroutine has visibility of that particular local variable L. Nobody else can see it. Okay, so now let's go ahead and get started. The first line outside of the definition of a subroutine is line 6, and we will initialize x to 10, and then we get to line 7. Line 7, we'll do the usual stuff. You guys know the drill already, right? When we invoke a subroutine, there are two things to do. So exactly what two things do we have to do?
Return line
Yep.
RT line.
Okay, we allocate the leftmost available column for our return line number, right?
Yeah, why is it left?
Why is it the leftmost? Because I just have to pick an order. It's either the rightmost or the leftmost. It can only go in one direction.
Because you click on the right.
Right, because if I choose the rightmost available column, that will be like way off the screen, right? So that makes it harder to visualize everything. If I pick the leftmost, then it's right next to X and it's easier to, look at it. It's visually easier to keep track of it. Okay?
This is for this class, but this is actually just memory allocation.
These are basically all memory locations when we get to the assembly programming class. Yep. So we allocate the leftmost available column. We label it return line number because that's how we're going to use this column. And then we'll say, okay, which line am I supposed to go back to when we come back from the subroutine? Post. Exactly, because there are no more lines of program after line 7. And then we say, okay, what is the second thing we have to do when we invoke a subroutine? We continue execution in the subroutine starting from the beginning of the entire subroutine. Okay. So that means, in this case, we continue execution on line 3. Hold on a second here. We're missing something. What about that local variable L? Remember what I said? A local variable does not exist until the subroutine is invoked. What did I do? I just invoked a subroutine, right? So that means, hey, we're missing something here because the other thing we have to do is to allocate another column. Okay, another column, leftmost available, and this time it is for my local variable L. and all local variables start with an unknown value. Is that okay so far? Now, this is a new concept, okay? It is borrowing something that we already know, which is the dynamic allocation of the return line number column. But this time I'm allocating another column, not for the purpose of returning or specifying where I'm supposed to return to, but for the purpose of my local variable, which is variable L in this case. And all local variables start with an unknown value. Now this is very important. So that means, in any test, if I give you a trace of a subroutine with a local variable, the question mark is worth some points because it is a very important part of understanding that local variables have this particular critical attribute. They always start uninitialized. Okay. On line 3, we are going to copy x to L. Now that we have allocated a column for L, can you guess what's going to happen on line 3?
D is going to get updated to 10.
Column D is going to be updated to a value of 10. Exactly. Okay, because at this point, variable L does exist and it is visible to the subroutine useless. Okay, so that's all good. Okay, it seems like useless. It's not that useless. I mean, we are doing something to the trace. Okay. Then we move on to line 4. Line 4 is an assignment statement. The right-hand side is L times 4. So we look up L, it is a local variable, it is now living in column D, it has a value of 10. 10 times 2 is 20, we want to store that back into L, and once again L is living in column D, so column D is now updated to a value of 20. No problem, I think most people probably can guess what's happening with line 4 once I explain what line 3 is doing. Now we get to line 5, which is kind of interesting because line 5 is and define sub. We are at the end of a subroutine. At the end of a subroutine, we already know what we usually have to do, right? We look up the rightmost or the most recent return line number, use it to tell us where we continue execution. So we'll go ahead and do that, no problem. So we will do exactly the same thing as we always do, and then we say, oh, this column is no longer in use. Let's go ahead and deallocate it. Okay, so we'll go ahead and use a strike through symbol to indicate this column is now deallocated. Do you remember what I said about local variables? They only start to exist when the subroutine is invoked. What do you think happens when the subroutine is done and it's time to return?
They cease to exist.
It will cease to exist at exactly that moment. So that means I also have to deallocate column D in this case because a local variable will cease to exist when that invocation is done. Okay. So I'm going to do exactly the same thing here. So I'm going to say copy, paste, and then change the format to a strike through. So this time I'm allocating 2 columns every time I invoke useless, and I'm also deallocating 2 columns every time I return or get out of the subroutine useless. Okay? And then we continue execution at post. So by the time I get to post, which is the conclusion of the execution of the entire program, column C and column D are as if they never existed because I allocated and then I deallocated. Do you guys now know why the subroutine is called useless?
Yeah.
Okay, but that illustrates how the behavior of local variables. Okay, it's really quite interesting. It's useful because it is local not only to the subroutine, but local to an invocation of a subroutine. Okay. When I refer to the terms a subroutine versus an invocation of a subroutine, is the distinction clear, or is it kind of like, yeah, I kind of have an idea of what it is, but not exactly? I can give you one analogy, and that will make it kind of clear. Okay, so let's say I'm moving, okay, and I'm going to the U-Haul place or whatever place I can rent a truck, and I rent a truck. Okay, the truck is a subroutine, and I am an invocation of a subroutine. All right, so excuse me, I need to I thought my phone is turned off, but it's not. Okay, so I'm gonna turn it off now. Sorry about that. Okay, so I'm a invocation, and then the subroutine is just a truck. So let's say I'm driving my truck, and I have a few days to do my moving, okay? And the first person, and then I ran into you, okay? And then you say, well, Tag, I'm also moving, and I could use a truck. So I'm thinking, hey, if I can sublet the truck to you, for a few hours or for a day or two, we can share the cost of the truck, right? So it's good, okay? So I'm going to sublet the truck to you. So you are now, quote unquote, the second renter of that truck, okay? You are the second invocation. How many trucks do we have? There's only one truck, okay? But now we have two people, quote unquote, renting the truck at the same time. So you drive the truck, around, and then you meet another friend of yours, and then you say, oh, I know you're moving today too, so I can save some cost by subletting the truck to you. So then that person becomes the third renter of the truck, and that's equivalent to the third invocation of the same subroutine. Okay? So that means when that person is done with the truck, that person is not going to return the truck to me, because that person only knows you, so that person returns the truck to you. So now, by that time, we only have two invocations left with that subroutine. When you're done with that truck, you return it back to me. So I will finish up my moving. When I'm all done, I return the truck back to U-Haul. So the truck is still there, but at that point, after I return the truck to U-Haul, there are no one renting the truck at that point. So the subroutine is still there, but there's zero invocation at that point. So is that okay so far? And invocation is kind of more of a dynamic thing. It depends on at what time we are talking about, but the subroutine itself is always there. Okay. Now with that in mind, we're going to rewrite the factorial program. Remember, we have a recursive version of the factorial program. I'm going to rewrite it to make use of local variables. You will see factorial rewritten quite a few times, because every time we introduce a new concept, we'll rewrite the factorial program to make use of that new concept. We are now explaining local variable. The next thing is to explain what is a by value parameter, and then we'll explain what is a by reference parameter, and then we'll explain what is a return value. And all of those will prompt a revision of the factorial subroutine. All right, so let's go ahead and redefine our factorial subroutine here. And then what we'll do is to say, this time we're going to have a local variable. And I'll just call this local variable x. And in the first part of the program, we still have a conditional statement. The conditional statement is still saying, okay, I'm supposed to find the factorial of n, so I need to know whether n is 0 or not, because if it is 0, I know the answer right away. It is n factorial is 1, because 0 factorial is by definition 1. So I can say, I'm going to change the flow of the logic just a little bit here. So I would say if n equals to 0, then I know the answer. The result, which is still a global variable r, is going to be just 1. Okay, no big deal, kind of the same as last time. I just flip the polarity of the condition compared to last time. Else means when n does not equal to 0. Now we have to assume that n is non-negative, and also it has to be an integer, because otherwise it doesn't make sense to find a factorial of n. Well, if n is non-negative, is an integer, and yet it is not 0, that means it's a positive integer. Okay? If it's a positive integer, I can do one thing. I can say, hey, I may not know how to compute n factorial, but I know the steps to do it. So what I'll do is I'm going to say, let's decrement n by 1, so we are changing the problem to a one-step smaller problem. Instead of finding n factorial, I'm saying, let me see if I can find somebody else to find the factorial of n minus 1. Who can find the factorial of n minus 1? Hey, I know. is the subroutine called factorial. Okay, we'll go ahead and invoke factorial. But before this, I'm going to use another thing here. I'm going to insert a row before we change n. I'm going to save it. I'll say, hey, you know what? I'm going to use my local variable to save, n. And then I'm going to change n, and then I will go ahead and invoke factorial. When factorial comes back, r is supposed to have, the factorial of n minus 1. In the previous attempt, we have to add 1 back to n in order to figure out what is the factorial of n itself. But this time, because I already saved the value in x, I don't have to do that anymore. So I can now just say that r is x times r, because x was x is storing the old value of n before I perform the decrement. Okay. And then we say and if, and define sub. That's my new subroutine. Just making use of a local variable. And then the next thing we'll do is to figure out how do we trace something like this, because it has local variables. All right, so we'll go ahead and try it again this time, and I think we'll not really go for the, well, maybe we'll go ahead and do that. Same thing. So n starts with a value of 3, and then we invoke factorial. And then we'll try to find out what we are going to do in this case in our trace. So, rid of this, and then make a new window of this document. All right. And this time we do need a column for comments and the usual line number. And we still have global variables here. Other than x, everything else are still global variables. So we have n and r still being global variables. They exist from the very beginning of the algorithm's execution, and they only cease to exist after post. So n and r basically are always there. They start with unknown values, and that's my precondition. So it doesn't seem like we are making a whole lot of differences this time. Not yet. Okay, on line 12, because line 12 is the first line outside of the definition of a subroutine. Yep.
Where's R outside of the sub?
Where's R?
Outside of the subroutine.
Why is R outside of the subroutine?
Where is it outside of that?
I'm not referring to it because it's only going to store the value of n factorial.
Wait, since it's inside of the subroutine, wouldn't it be getting? Shouldn't it only be there once it gets in? The subroutine gets involved. So what you're saying for the other example was that it's when the variable has that title local, like x, for instance, but in the example with R, though it's not titled x, local, it's still in the body of the subroutine.
Well, a subroutine can refer to local variables and global variables. It can access both kinds. Global is still global. I mean, we can still access any global variable anywhere in the algorithm.
But I guess what I'm saying is n is I guess in its own declared global because it's outside of.
N and R are both global because neither has a local to it. So they're both global by default.
Okay.
Okay. So I'm using the same convention, as in earlier parts of the class, where variables do not need to be declared. We can just start to use a variable, and it becomes a global variable. All right. So this is line 12. No big deal. And then on line 13, we will use exactly the same approach as last time. The invocation has 2 steps. Step 1 is to allocate the leftmost available column for the return line number, and then remember where we're supposed to return to. In this case, it's post. And then we continue execution in the subroutine starting on line 3 in this case. But we also remember we have a local variable now, so x as a local variable is also allocated at the time of the invocation, but x as a local variable starts with an unknown value, so it is always a question mark. Then we continue execution on line 3. Line 3 is comparing n to 0. Oops, I forgot one thing, didn't I? On line 12, I'm supposed to change n to 3. So that's why it didn't make sense. Okay, so n equals to 0 is false. We have to go to the else branch. The else branch is starting on line 6. On line 6, the first thing we do is not to change n, but to save the value of n in our local variable x. Well, we have seen something like this already in the useless example, right? Okay, no big deal, we can do that. We just copy the value of n, which is 3, to x. So now column F, which is the variable x for this invocation of factorial, will end up with a value of 3. Then we move on to line 7. Line 7 is going to decrement n by 1, so n goes from 3 to 2. And then we go to line 8, which is the invocation of factorial. We know the drill by this time. We allocate the leftmost available column. In this case, it's column G. Remember where we are supposed to go back to, since the invocation is on line 8, and we do have line 9 following line 8 that has something to do. So the return line number is line 9. And then we continue execution at the beginning of the subroutine, which is on line 3. But we also remember we have a local variable x to deal with this time. So we're going to say, okay, we have a local variable x, and as all local variables, it starts with an unknown value. So column G and column H are now allocated by the time we get to line 3. But we're still doing okay so far at this point. Okay? So it's not much has changed, since the previous implementation of factorial. It seems like column F is handy, but I'm not quite sure how it is used. But that's okay. We'll just continue with this trace. N equals to 0 is false because n at this point has a value of 2. We move on to the else branch on line 6. Yep.
Since we're still in the subroutine, wouldn't the program actually cancel the value of the first x? Means that
Nope. Every invocation gets its own x. Okay. So that's really important. Okay. Because every invocation has its own version of local variable x, and they are independent. It's just kind of like in the example, when we have, the truck rental example. Every renter of the truck has a driver's license. Okay, so that's kind of what it is, because invocations can have its own things. It has its own, data. Okay, so on line 6, we are going to say x gets n. Now this is starting to get a little bit confusing because we have column F, labeled x, and then we now have column H also labeled x. So which x do you think we are talking about?
H.
The rightmost, right? Column H is the correct answer. So we always refer to the rightmost one when we refer to local variables. In fact, at this point, the other x, which is on column F, is completely inaccessible by this invocation. It's just like, when I sublet the truck to you, okay, you are the second invocation, you have no access to my driver's license. When you get pulled over by the cops and they ask you for the driver's license, you pull out your own driver's license. You're not going to pull out my driver's license. Okay? Is that okay? Because I think that's a really interesting example, because that's exactly what it is. Because each invocation has, quote unquote, its own driver's license. So when we refer to, okay, you have to present your driver's license, whose driver's license are we talking about? The one of the current invocation. Okay? Not the person that you borrowed the truck from. Okay. So on line 6, we are now copying the value of n, which is 2, to column H, because column H has the most recent version of local variable x. So now this guy is going to get the value of 2, and then we move on to line 7. Line 7 is decrementing the global variable n by 1. It goes from 2 to 1. We go to line 8. We are invoking the subroutine again, and by now it's pretty much the same stuff, right? I mean, we have to allocate a column for the return line number, Because the invocation is on line 8, the return line number is going to be line 9. In this case, we do have something to do on line 9. And we also have to remember to allocate for variable x. Because it's a local variable, it always starts with an unknown value.
And this
So-
is not overloading x at all.
It's not overloading. It's not overloading.
Okay.
Okay. And then we get to the beginning of the algorithm or the subroutine again on line 3. So at this point, we have 3 invocations of the same subroutine. In our analogy, there are 3 renters of the same truck. Okay, we're on the 3rd person now. On line 3, we'll do the same thing. We compare the global variable n to 0, and it is non-zero yet. We move on to line 6. We make a copy, and by now we also know that even though we have quote unquote many copies of x, we always refer to only the most recent one. In this case, it's column j. So column j gets a value of 1, and then we go to line 7. We decrement n by 1. It becomes 0, and then we invoke factorial again on line 8. So nothing really too mysterious, at this point anymore. I'm going to change the zoom just a little bit so that we can show the last 2 columns. And then we have, the usual stuff. Return line number is line 9 because the invocation is from line 8. And then we have local variable x initialized or non-initialized at this point. That's why it has a question mark. And then we continue execution from the beginning of the entire subroutine again on line 3. N equals to 0. This time is true because the global variable variable n does have a value of 0 at this point. If the condition is true, then we go to the then branch, which is on line 4. Line 4 doesn't have much to do except to update our global variable r to 1. So r is now getting a value of 1. Are there any questions at this point? Because the recursive call is stopping here. Okay. The only time I'm going to do a quote-unquote recursive call or invocation is when we can get to line 8. This time we are using the then branch, which means there's no way we can continue the recursion. We're going to unwind everything that we have done up to this point. Are there any questions at this point? Okay, no questions? All right. If there are no questions, we are now getting out of our conditional statement. And guess what? Up to here, up to row 23, this is the first time that we get out of the conditional statement. Because we were stuck in the conditional statement, in the else branch, multiple times. Because each time in each invocation, we were stuck because of the invoke on line 8. So this is the first time we actually get out of the conditional statement and end up on line 10. Nope, line 11. On line 11, we kind of know what to do because we just talked about it in the useless example, right? We look up the rightmost return line number that is still active. In this case, it's column K. It tells us to continue execution on line 9. Good. And then we deallocate not just one, but both of the columns corresponding to this invocation. So we say format cells, strike through, and now we have deallocated both column K and column L. So this is also important to remember the return line number and also all local variables are on a per invocation basis. Each invocation has its own. You allocate per invocation, you also deallocate when the invocation is done. So we now get back to line 9. Now line 9 says we want to compute the product of x and r and then store it into r. Which x are we talking about? We still have quite a few x's on the spreadsheet right now.
Rightmost.
The rightmost, exactly. Okay, it's the rightmost quote unquote active column that is labeled x. In this case, it's column J because column L is gone. It is already deallocated at this point. So column J is the most recent one. It has a value of 1. And this is a good time to split the screen a little bit so that we can look at both the top and the bottom. So I'm going to split it like this. There we go. Okay. So on line 9, we have r being 1. We have x being 1 as well. 1 times 1 is 1, we store it back into R. So it, R basically gets quote unquote updated to a value of 1. After line 9, we get out of the else branch of the conditional statement. We end up on line 11 again, and we're going to do exactly the same thing. We look up the rightmost return line number. In this case, it's column I. It tells us to continue execution on line 9, and then we deallocate both of those columns. So I'm just being lazy here and copy and paste the strike through version, the struck out version. And then now we are onto line 9 again. Line 9, once again, is trying to compute the product of x and r. R is easy because it's a global variable. It has a value of 1 at this point. Let me scroll a little bit here. At this point, columns I, J, K, and L are all deallocated. The rightmost column corresponding to x is column H. Column H has a value of 2. 2 times 1, which is our R, is 2. We store it into R, so now it is updated to a value of 2. Are we still doing okay so far? As we are unwinding the columns. Okay. And then we continue execution. Okay. We get out of the else branch. We continue execution on line 11 again. Line 11 is going to look up the rightmost return line number that is still active. At this time, columns I, J, K, and L are all deallocated. The rightmost one is going to be column G. It's telling me to continue execution on line 9, and that's what we'll denote here. Let me answer your question.
Roll.
Okay, thank you. I didn't make a new row sheet today, so just write initial next to the previous date, and that will be fine. All right, but we forgot to do one thing on line 11. We have to deallocate the columns. At the end of a subroutine, we have to deallocate everything that was allocated on a per invocation basis. Oops, wrong place. Two down ones. Okay, there we go. All right, so you can see it's kind of getting boring at this point because now we're back on line 9, and line 9 is going to do its computation, the product, and then store the value. The question is, which x are we now talking about? Because G and H are now deallocated, so the rightmost column that has a label x is now column F. It has a value of 3. 3 times R is 6. We store 6 back into global variable R, and then we get out of the else branch of the conditional statement, continue on to line 11, which is the end of the subroutine, and then we do exactly the same thing. We look up the rightmost return line number, which is column E at this point. It tells us that we have to continue execution at post, and after we make use of that information, we deallocate those two columns, and then we continue execution at post, which means we are now at the finish line. There's nothing else to do. All right, so are there any questions about local variables? Go ahead.
Two things. First, does it matter to put return line number and then the local variable?
In this class, it doesn't matter. In cisp 310, it does matter because it's actually allocated in this particular way. But in this class, it's not important.
Okay.
I usually just put return line number first because that's the first concept that we talked about. So we just use that particular order.
And
Yep.
the second thing, are there only global and local variables, or could you have like a variable that is global to a subroutine only? Like, so it hits
That's a
every
very tricky
invocation?
question. Okay, that's a very tricky question. There are global variables and then there are local variables. But then there are two more things that we have to talk about. One is called a parameter, by value parameter, and the other one is called a by reference parameter. Okay, so those things are kind of like local variables, but not quite. Okay, one is almost exactly like a local variable. The other one is a way to kind of cheat your way out, so you can actually refer to somebody else's variable, but without using global variables. So when we get to that, we'll explain that. But at this point, just for local variables, is that concept okay? Okay. Okay, so remind me again, why is a local variable local? In what sense is it local? There are two.
Only while it's active.
Only while it's active. So in terms of lifespan, it is local to the invocation of a subroutine. What about the other part of the local?
It only exists until before the post. It only exists in the subroutine. After post, it doesn't exist.
Okay, he said that about the invocation, but what you meant might have been what you said. Did you mean only within the subroutine you can see you have visibility of the local variable?
Yeah.
Okay, so that's a scope. Okay, so we have lifespan as one, which is when does the variable start to exist and when does it stop existing. That's the lifespan, which is localized to the invocation. The other one is called scoping, which means which part of the program can see the local variable. Okay, that's basically just saying, okay, certain lines have access to local variable x, other lines do not have access to local variable x in this case. Okay, all right, that's all going good. Very useful concept. And let's move on to by-value parameters. Okay, this is the natural order of these topics. So we'll go ahead and talk about by-value parameters. And I do want to talk about that concept before we end today's class, because a by-value parameter is almost like a local variable with one little difference. Okay, so I'm going to use another spreadsheet or another algorithm to illustrate that point.
Out of curiosity,
Mhm.
is there like a website with just like a whole bunch of algorithms on there? Just kind of sitting there for you to kind of copy and paste or anything?
It's called Wikipedia. Yes. Okay, so we'll have another subroutine here, and we'll call this not so useless. Okay, so not so useless is going to have a by-value parameter. So instead of saying by-value parameter, we just say by-val. Okay, it's a short abbreviation of by-value parameter, and we'll call that, let's say, call it n here, and it will say x gets the value of n, and define sub. Okay, so this is my subroutine. It is not so useless. And it is rather strange because I said by-value parameters are almost like local variables, right? So a local variable starts with an unknown value. And in this code, x is a global variable. It is not local, nor it is a by-value parameter, and therefore it is global. So it seems like x is going to get an unknown value. I mean, how useful can a subroutine like that be? Making x unknown, basically. Okay. We'll take a look here. When we invoke this particular subroutine that has a single by-value parameter, we use basically the same way. Basically just say invoke and then the name of the subroutine. But we then say something else. The invoke statement now can specify the start value of the by-val parameter. Okay, now this is a big difference between a local variable and a by-val parameter, because the invoke statement, not inside the subroutine that we are invoking, can now say, you know what, I want n to start with a value of 5. Okay. Now this syntax is only used in this class. In all of your other classes, we just say 5. Okay, it is implied that it is by position. Since we only have one by-value parameter, the 5 will automatically be feeding the only by-value parameter. But in this class, I make it very explicit. So we say 5 is the initial value of the by-value parameter n. Okay, that's it. Okay, that's my little sample program here to illustrate the basic concept of a by-value parameter. And we'll go ahead and open the new window to trace it. The trace is very important when we are dealing with subroutines and these concepts, because it really illustrates what is happening behind the scenes in and therefore we know why the program behaves in a certain way. Line number and x, they have to be here. The precondition is I know nothing about x. X starts with an unknown value. And then the first line, the only line that is outside of the definition of a subroutine is line 5 itself. And now we go through the invocation. Just as any other subroutine, okay, we have the return line number allocated as the leftmost available column. And in this case, because we do not have a line 6, the return line number is post, which basically means by the time we return, we're done with the entire algorithm. So that part is identical. And we even have the same thing here to continue execution at the beginning of an entire subroutine. So this part is consistent since the beginning of the discussion of subroutines. Okay, nothing has changed regarding the saving of the return line number and also continuing on the first line inside the subroutine that we're invoking. The second part is kind of like a local variable because now we also have to allocate a new column, in this case column D, which is the leftmost available column after we allocate for the return line number, and we call it n, okay, it has a label n here. But unlike a local variable, n does not start with an unknown value. It starts with a known value because it is specified by the invoke statement itself. So in this case, the invoke statement on line 5 specifically said that 5 should be the initial value of n, and therefore n starts with the value of 5. So this is why I said by value parameters are kind of like local variables with only one major difference. It starts with a known value that is specified by the invoke statement. Okay? It's not by an initialization inside the subroutine, it's from outside of the subroutine. Now that is really handy in many ways because we will have enough time to look at another revision of the factorial program, and this time you will see why by value parameters are really, really handy. Okay, so we get to line 3. Line 3 doesn't do anything that's mysterious. It just copies the value of n to x. N has a value of 5, so now x as a global variable also ends up with a value of 5. And then we end up on line 4. Line 4 has two things to do. One is to deallocate everything that was allocated for this invocation. Which column or columns is or are allocated for this invocation?
C, D.
C and D. Okay, very good. So that means the first thing we do is to look up the return line number. Just make a note so that we know where to continue execution. And then we deallocate both columns. This part is the same as a local variable because local variables have exactly the same properties. We allocate on a per invocation basis. After the invocation, we deallocate. Same thing here. In terms of scope, which means which part of the program can see this particular variable n, it's also the same. It's only within, in this case, our subroutine not so useless. In other words, only from line 2 to line 3, well, in this case, only line 3, only line 3 has visibility of the parameter by value parameter n. And that's it. Okay, this is our by value parameter.
So the major difference between the two is that you can initially assign one or assign a value to a by val with your invoke statement, but you can't do that with a local variable.
That is correct.
Okay.
Yep. A local variable, you can see it as a scratch paper inside an office. Okay. It is only accessible to the person inside the office, but the outside world cannot, see what the paper is, cannot, give it an initial value.
Okay.
A by value parameter, on the other hand, is kind of like an inbox. Okay, it allows the outside world to pass information into a subroutine. So it's an inbox mechanism. Okay. All right. So what we'll do now is to rewrite the factorial program again, but this time make use of by val parameters. So once again, we define subroutine factorial. This time we say by val n. Okay. And the rest of the program looked about the same. We say if n equals to 0, then the result, which is r, which is still a global variable, gets 1 because 0 factorial is 1. Else, which means n is positive, a positive integer. Then we say r, well, the first thing we have to do is to invoke factorial again. But this time when we invoke factorial, we don't have to decrement n first, because we can now specify something like this, which is awfully confusing. Okay, we'll get to that part next. Okay, when the factorial returns, r is going to have the value of n minus 1 factorial. So get to n factorial, we just have to say r gets r times n. Okay, we don't have to do a single thing to n. And if n define sub, and in this case, I don't have to initialize n anymore. I cannot say, outside of the definition of the subroutine, I cannot say n gets 3. Why not? Why can't I say n gets 3 in this case?
Because it's only known by the subroutine.
It is a parameter of the subroutine, so the scope is limited to inside the subroutine only. Any code outside cannot refer to it. Okay, that's one reason why I cannot refer to n. And the second reason why I cannot refer to n is simply because n has not even existed yet. Remember, n is a by-value parameter, but like local variables, it does not exist until we invoke it, the subroutine that contains it. At this point, I'm not invoking anything, so n has not even existed yet. Okay, it is not there yet. So I don't have to do something like that. I can just say invoke factorial, and because we are slightly running out of time, I'm going to start with something really simple first, and then we'll talk about something a little bit more difficult later. Okay, we'll start with n. 1 specifies n in this case. And then we'll go ahead and finish this algorithm. Do you see factorial getting a little bit cleaned up? In other words, it's a little bit shorter now. We start a new sheet here. We have conditions to evaluate line number, and we still have one global variable r. Okay, r cannot be removed until we get to return values. Okay, so it will stay there for a little bit of time. The precondition is r starts with an unknown value. Then we get to the only line in the entire program outside of the definition of a subroutine, which is line 10. Line 10 is going to say, I will save the return line number as post. I will also, allocate another column for parameter n, and it starts with a value of 1, because the invoke statement is specifying that value of 1. Then we continue execution inside the subroutine on line 3. N equals to 0 is false, so we continue execution on line 6, which is another invocation of the subroutine. The first part is easy. We have to allocate a column for the return line number. And because the invoke statement is on line 6, and we do have another statement on line 7, the return line number is going to be line 7. And then we also have to remember that we continue execution in the subroutine starting on line 3. The mysterious part is, what do we do about parameter n? Because the specification looks somewhat confusing here. If you look at this part here, what are we actually saying? Which n are we referring to when we say n minus 1, and which n are we referring to on the other side of the right arrow in this case?
So the left-hand side's referencing the one that's already there, and then the new one's going to be the ones
that we are creating at this point. Exactly. So what this symbol is saying is, I am creating the new parameter n. So the n, sorry?
Based off the old parameter?
Yep.
Okay.
So the one on the right-hand side of the right arrow is referring to column G. That is the one that we're trying to specify at this point. But the expression that is going to specify its value is n minus 1, which is the left-hand side of the right arrow. That n cannot possibly refer to column G, because column G is the one that I'm trying to specify. So that n on the left-hand side is now referring to the n that I still have visibility of, which is column E. Are we doing okay so far? That's why this guy gets a value of 0 because it is this n minus 1 to specify the new n. Okay? Any questions about this mechanism? Well, since it's all getting recorded, so that means you can review it. This is at the end of the entire class. That makes it kind of easy to find too. Okay, so now we're back to line 3 at the beginning of the entire algorithm. N equals to 0 is true because this n refers to the most recent n, the column that is labeled n, and which is also known as the rightmost. So in this case, the rightmost column with the label n is column G. It has a value of 0. 0 equals 0 is true. We execute line 4. R gets a value of 1. And then we get out of the conditional statement. We end up on line 9. Line 9 is going to do exactly the same thing as it usually do. We look up the rightmost return line number. It tells us we have to return to line 7. So we make a note of that, and then we say both of these columns, everything that we allocated for this invocation of the subroutine are now deallocated. And now we continue execution on line 7. Line 7 wants to compute the product of R and N, and then use that to update R. R is easy, it's a global variable, has a value of 1 at this point. Which N are we talking about now? Column E, because column G is now gone. Okay? So column E becomes my rightmost column with the label N, and that has a value of 1. 1 times 1 is 1, and that's why R is once again updated to a value of 1 on line 7. Then we get out of this loop, we get out of the conditional statement. We end up on line 9, and then we do the same thing. We look up the rightmost return line number that is still active. This time it's column D. It tells us to continue execution at post. And then we have no use of both columns anymore, and they're both deallocated. We continue execution at post, finish line, we are all done. So as a brain teaser, I know you guys like to do stuff over a long weekend. As a brain teaser, I want you guys to make this just a little bit lengthier. Specify 3 instead of 1, as the parameter n for on line 10. We can the rest of the program can remain exactly the same as it is now. Just change it to invoke factorial. 3 specifies n, and then see what happens. I know it's going to be a little bit tedious, but that really helps to kind of make you think about it and make use of the concept that we just talked about today. Have a nice weekend, and I'll see you guys on Tuesday.